Hello and welcome to our discussion on momentum. Momentum is the motion, the force that comes with motion. It's calculated by multiplying the mass of the object that is moving times the velocity, not the acceleration. So the difference between force and momentum is that force from Newton's second law of motion, force equals mass times the acceleration. But the momentum is not mass times the acceleration. Momentum is mass times the velocity. So very interesting. Now, when we hear that the force equals the mass of the moving object times the acceleration, then if we want to calculate the momentum of that same object, what can we do now? Well, we already know that the acceleration equals velocity divided by time. And we already know that momentum is mass times velocity. And we know that the force equals mass times acceleration. So if I divide my acceleration by the time, that will give me the velocity. So in other words, dividing the force by the time will give me the momentum because that will give me the mass times the velocity. And we will learn more about that. So vehicles have safety features like the airbags and the seat belts. So what happens here is that at a moment of impact, at a moment of collision, the car is moving with the mass of the car, which happens to be m1. That's the mass of the car. The car is moving with a velocity v1. So the car has a mass. So obviously, we're not talking just about the car. We're just talking about the whole moving system, which includes the car, the person driving the car, the goods that are in the car, and we are speeding with a particular velocity. If we need to calculate the momentum, we multiply the mass of our whole system, our car, the people inside the car, and all the goods that are inside the car. We multiply that will be m1, the mass of everything that's moving. We multiply the mass by the acceleration of the car. That will give us the force, the potential force of that car. If that car hits you, if that car hits you, God forbid, that car will hit you with the mass, which is the collection of all the masses that are in this car system times the acceleration of that car. But if that car hits you, it will hit you with a momentum that will equal the mass of the car and everything that is in the car times not the acceleration, because that will give you the force times the velocity multiplied by the velocity. So these airbags are helpful because we know that time is a component in our momentum. You know that time is a component in our momentum. How is that? We already mentioned that force, let me write that down. Force, we already mentioned that we have already mentioned that force equals the mass of the object multiplied by the acceleration. And we know that the momentum momentum is referred to as P, equals the mass multiplied not by the acceleration, but by the velocity. But we already know that acceleration is itself, so we can rewrite this formula m times a as m times, and we replace acceleration by velocity divided by time, because that will give us the acceleration. Now, the momentum we know already is the mass times the velocity. So can I rewrite momentum in terms of force? Of course I can. So I know that my momentum must equal my mass times my velocity. Now let me rewrite my velocity. I will rewrite my velocity as, so if my acceleration equal velocity divided by time, then I could multiply, so I know my force, I can multiply my force by the time. So I can take this formula right here, and I know that my momentum is m times v, which is the same thing as the force. The force is mass. The force, let me copy that. The force is mass times velocity divided by time. Then I'm going to go ahead and multiply by the time. So the time can cancel out. So I know that velocity divided by time is acceleration. And acceleration multiplied by the time will give me velocity. So I know my momentum is m times v, which is the same thing as m times velocity divided by time multiplied by the time, which is the same thing as the mass multiplied by the acceleration multiplied by, because I know what's in parentheses here, that's the same thing as acceleration. But we're going to write acceleration as velocity divided by time. And then we multiply it by time, time will cancel out. And then it's the mass times the acceleration times the time. So now my airbag, what will my airbag do? My airbag will influence the time. So when you are in a car accident, God forbid, you cannot change their mass. Your weight is the same. Your car mass and weight is the same. The acceleration of the car is the same. But when the airbag and the seat belt are intact, they will increase the time. They will increase the time it would normally take. So without a seat belt, without an airbag, the moment the collision happens, your mass and acceleration will hit the wheel and will hit the glass. But because of the car airbag and because of the seat belt, they will hold you back, delaying, increasing the time. And when you increase the time, you know the momentum is conserved. You cannot change momentum. So your mass cannot change, your acceleration cannot change, but when you increase the time, the force is going to decrease. The force is going to decrease, and that will minimize the impact through which you will hit that car wheel that may hurt you. So now let's look at here. We look at this system. Don't just say a car. This is a car, people inside it, and goodies. We call that M1. This is car number 2, and the people inside it and all the good stuff that they have inside the car, M2. And each car has its own momentum because it has its own mass and its own velocity it's going with. As long as you have a mass, as long as you have a velocity, you bet you have a momentum. So car 1 going with the velocity 1 has a momentum P1. Car 2 has mass M2 and it's going with a velocity V2. They will have a momentum P2. So this is the momentum P2, that it has its own momentum. Now, when we examine this, we examine it with, we look at the entire 2 cars as 2 separate systems, and they will give me in the end a total momentum. So the total momentum is conserved. You cannot change it because the net external force acting on the 2 cars is 0. It is the cars who have their own unique individual momentum. It has its own mass, own velocity, and this car has its own mass and own velocity. So here it's telling us that car of mass M1 moving with a velocity V1 bumps into another car of mass M2 and a velocity V2. As a result, the first car slows down to a velocity of v1 prime. So after the collision, that's before the collision, we just have p1, and after the collision, we have p prime. So prime is your momentum after the collision. But remember, before collision, after collision, the momentum before the collision and the momentum after the collision are obviously different. Your momentum before you get into a car accident and your momentum after you get into a car accident is the same, but the total momentum is conserved. So your momentum before going to collision is different. I'm sorry, it's not the same. Your momentum before going into a collision is different because your speed is different, your velocity is different, your mass is unique to you. And the other car, it has its own unique mass and its own unique velocity. But when they collide, after that, they will have a momentum that is also different. But the total momentum before the collision and after the collision has to be conserved, So as a result, the first car is going to slow down to this velocity v1, and the second car is going to speed up to a velocity v2 prime. The momentum of each car is changed, but the total momentum, p tot, the total momentum of the two cars is the same before and after the collision. Obviously, if you assume other forces like friction is a force, remember? It's a force that is fighting fighting the wheels, preventing them from moving forward. It's the same before and after the collision if you assume friction is negligible. So that's your first system, is who's hitting who before the collision. Your after is going to represent who have been hit after the collision. So car 1 has its own momentum, car 2 has its own momentum, and after the collision, each car has its separate momentum. But you must appreciate that before the collision and after the collision, they have the same momentum. Now, we talked about this is a linear momentum in one direction. You hit a car vertically, you hit a car horizontally. But what if we're spinning or rotating? Does that mean satellites are not supposed to collide with each other who are spinning or rotating around Earth? They're not supposed to hit one another? So obviously we have two kinds of momentum. There is a momentum that is linear in one dimension, or a momentum that is angular, going around in a circle. So here we see that an ice skater is spinning on the tip of her skate with her arms extended. So L is the angular momentum, while I is her mass, her inertia, and omega is the velocity. You know, momentum, linear momentum is a P, but angular momentum is an L. Mass in linear momentum is an M, but the mass in the angular momentum is going to be I, inertia. And the velocity in linear momentum is going to be referred to as a V, while the velocity in angular momentum is going to be referred to as omega. That's the angular velocity. So her rate of spin increases greatly when she pulls in her arms. Why is that? Why is it when the figure skater pulls in her arms to her core, to her center, she's going to spin faster? Well, if you look at the mass, when you bring in your arms to the center, you decrease the inertia, you decrease the mass, and you decrease the amount of air resistance that you are exposed to while you are spinning. But when you bring them in, you're going to decrease the mass. You're going to decrease the air resistance fighting your body, and that's going to obviously, because the momentum is conserved, whether you're spinning with your arms wide open, extended, or you're spinning with your arms tucked in the end, L is conserved. When L is conserved while your arms are extended, the inertia is going to be high and omega is going to get low. So your speed speed of rotation is going to drop. But when momentum is conserved and the inertia decreases because now you're pulling your arms inwardly, then the omega is going to increase and the velocity of you spinning is going to increase so much. Now, this diagram shows a one-dimensional elastic collision. What's an elastic collision? Elastic collision must fulfill certain criteria. The first criteria is that it must be between two masses. Obviously, you're not going to have a collision unless you have at least two masses. And then the collision must be in one dimension. So you're moving in a highway, you hit a car in front of you, or you get hit by a car behind you, God forbid, or something like that. It must happen in one uniform dimension. And the elastic collision means that after the two bodies collide, they don't stick together. They don't glue together and move together. Each one has its own separate, unique path after the collision. So you will see that not all the collisions, you will have the two bodies colliding and each one will go their own way. Sometimes you will have collisions where you will have the two bodies stuck together. They will be stuck together and they will move together. So this is an example of a one-dimensional in one direction, as you see here, x-axis, even though they're moving in two different directions within the same dimension. So that's the x-axis. One is moving from the west to the east. The other one is moving from the east to the west. But in the end, east or west, this is not vertical. This is not north or south. This is east and west. That is the x-axis. So this is one-dimensional. And both of them, when they hit after the collision, one went backward in the opposite direction, and one went also backward in the opposite direction. So they didn't stick together. So if they don't stick together, that means they are elastic. That was an elastic collision. If they get stuck together and move together after that, that will be an example of an inelastic collision. So this body has mass m1 going with a velocity v1 in this direction. This body has mass m2 going with a velocity v2 in that direction, and both collide. That's before. After they collide, they move in opposite directions. That's a perfect example of an elastic collision. You must also recognize that the net force acting on the two bodies during the collision has to be zero. That's our main criteria for momentum to be conserved. The external net force must be zero and the friction force must be negligible. You could assume that it's a frictionless surface. The last criteria for elastic collision is that the kinetic energy must be the same, must be conserved, must remain constant. If you have a collision in which the kinetic energy before the collision is different from the kinetic energy after the collision. If the kinetic energy after the collision is more than the kinetic energy before the collision, or when the kinetic energy after the collision is less than the kinetic energy before the collision, what's going to happen? That is not elastic collision. That is inelastic collision. So elastic collisions you must have the two bodies never glued or stuck together. And the second requirement, the kinetic energy before and after must be conserved the same. For inelastic collision, in the collision, both will stick together with glue, and the kinetic energy before and after will never be the same. That's inelastic collision. So a one-dimensional inelastic collision between two objects is shown here. Momentum is conserved. Obviously, momentum is always conserved, whether we're dealing with elastic collision or inelastic collision, but the kinetic energy is not the same. So let's compare elastic collision versus inelastic collision. In elastic collision, after the collision, each colliding body went its separate way. But in inelastic collision, after they collided, they got stuck together with glue. So that is an example of inelastic collision. The second law, so two objects of equal mass initially head directly toward each other at the same speed. The objects stick together, creating a perfectly inelastic collision. In the case shown in this figure, the combined objects stop. This is not true for all inelastic collisions. Sometimes they stop, stuck like that, and sometimes they move together. But in the end, they stuck together, you have already violated elastic collision. That is now an inelastic collision criteria. The second thing, you bet, when they stick together, the kinetic energy will not be conserved, like how it was here when they separated together in the elastic collision. They got stuck together. That's an example of inelastic collision, and the kinetic energy will be different when before and after. So now we obviously have the instances where not every single collision is one-dimensional. You just collide going from east to west, or you collide going from north to south. What if you're playing pool? You know, when you're playing pool, you hit with the white ball the blue ball, for example. And when you notice after the collision, they didn't move in the same direction. They didn't get stuck together. Each one moved in a different direction. So before the collision, mass one was moving along the x-axis. But after the collision, mass two covered some x-axis component as well as some y-axis component. So this is a triangle now. This is a triangle that has an x side and a y side, and this hypotenuse here. This hypotenuse here, this chord here, this hypotenuse here, remember from the Pythagorean theorem, we said that this angle, the sine of this angle is the side facing it divided by the hypotenuse. And the cosine is the side next to it divided by the hypotenuse. So this movement here, that is the hypotenuse. The movement of M1 is the hypotenuse of this triangle. And the movement of M2 is the hypotenuse of this triangle right here. This triangle right here is your triangle of which the movement from M2 to this position is your hypotenuse. So now this is a two-dimensional collision with the coordinate system chosen so that M2 is initially at rest. So M2 is 0, it's at rest, it's not moving. This one is moving. And V1 is parallel to so the velocity of which V1 is moving and with which it hits M2 is parallel to the x-axis. So now if I want to calculate my momentum, I have to calculate my momentum exclusively in the x-axis and my momentum on the y-axis. So now in the momentum on the y-axis, I have to get the x component and the y component of this blue ball. So if I want my x component, I know that the angle theta equals I know that the cosine of angle theta is going to equal this line that I want on the x-axis divided by the hypotenuse. So if I want to get this line, I multiply the cosine of this angle times the hypotenuse, and that will give me the exact x component of this M1 ball. And if I want to get so that will give me the velocity on precisely the x-axis. If I want the velocity precisely on the x-axis of this orange ball, this is my hypotenuse. I have its velocity v prime 2. So the v prime here is the velocity representing this hypotenuse of this triangle. And the velocity of this orange ball here, that's my hypotenuse. If I just want the x component of the v prime, this velocity, I'm going to have to divide the hypotenuse, which is v2 prime, and I have to multiply it actually by the cosine, because we know that if you want to get this angle here, that is going to be this line divided by this line divided by the hypotenuse. Okay, so this is a system of interest where we have this frictionless ice surface, and you have this puck here moving with mass 1, that its mass with a velocity in this direction. Then you have this player who's mass 2 and is going to move back once it's hit by this M1 puck, and they're going to move together as one system. So an ice hockey goalie catches a hockey puck and recoils backward. So what kind of collision is that? They are stuck together now. M1 and M2, they are stuck together and they move backward in an inelastic collision. So in order to get the momentum of this goalie before the collision, his velocity was a 0. So he wasn't moving. His mass is m2. Well, it doesn't matter because anything times 0 is a 0. So on that side of the equation, the goalie will not have a momentum. But this puck will be having a momentum that equals its mass times its velocity. Equals after the collision, you will have, so after the collision, you will have both of them, their masses added together, m1 plus m2, multiplied by the final velocity v prime of them moving together. So here you have two carts collide with each other so you see this cart is moving in this direction with this mass and this velocity. This car is moving in this direction with this mass and this velocity, and both of them collide, and this mass here is going to move in the other direction, and this mass is going to move backward, and that's an example of elastic collision. But you must understand, before the collision, the momentum before the collision of the two systems, the total momentum is the same. This mass can have its own momentum. This second mass can have its own momentum, but both of their momentums added together will give me the total momentum. After the collision, this mass is going to have its own momentum, and this mass is going to have its own momentum. Well, the momentum before the collision, P1 plus P1 here, so the momentum of both, this should be a 2. P1 plus P2 is going to equal the total momentum, and P1 prime plus P2 prime is equal to the total momentum, and both momentums are going to be equal. So I should have P1 plus P2 will equal P prime 1 plus P prime 2. So here, what do we have here? That's a bowling. So we see the same thing with the pool ball. So the incoming object of mass m1 is scattered by an initially stationary object. This is a stationary object. Only the stationary object's mass m2 is known. So now we know m2. So by measuring the angle and the speed at which the object of m1 emerges from the room, it is possible to calculate the magnitude and direction of the initially stationary object's velocity after the collision. So this mass here struck and hit this mass here. We don't know what this mass is, but we do know what this mass is. And we know that after mass 1 hit mass 2 curved with this angle theta. So before you have P1, so in the beginning, you have the momentum for the first mass, which is going to be represented by P1, which is mass 1 times velocity 1. But you don't have P2. You see, you don't have P2 before the collision because mass 1 had mass 2 had a velocity of 0. So if you went mass 1 times V1, mass 1 times V1 plus mass 2 times V2, mass 2 is a 0. So it will cancel out. Now you'll have mass 1 times V1 will equal mass 1 times V1 prime. That's our new speed. Plus mass 2 times V2 prime. So now I need to find out to calculate the magnitude and the direction of the initially stationary object's velocity after the collision. So I need to know the velocity after the collision. So I will bring mass 1 times V1, and I will equal to that mass 1 times its V1 prime, and I will add to that mass. So I have to get my x component. So my x component is the cosine of 45 multiplied by V1 prime, and that will give me the x-axis component of the velocity by which mass 1 is moving. Multiply that by mass 1. Add to that mass 2 multiplied by the unknown velocity of V2 and solve for the missing velocity. So we are very concerned. We are very concerned with understanding in this chapter. We talked about the concept of linear momentum, and linear momentum is often referenced as momentum and is defined as the product of the system mass. We talked about that. It's the mass times the velocity of the mass. So here, the mass that's m1 times v1, and this is m2 times v2. This is wrong. This should be m2 times v2. That's a typo in the book. This is the p1 is going to equal m1 times v1, and p2 is going to equal m2 times v2. We have learned that the SI unit for momentum is obviously the unit for mass, which is kilogram, multiplied by the unit for velocity, meters per second. Newton's second law of motion in terms of the momentum states that the net external force equals the change in momentum of a system divided by the time over which it changes. So that is going to be, obviously, we talked about that here, delta P, is going to be the change in momentum. The change in momentum divided by the time is going to give us the force. So if you divide this here, P, by T, is going to give you MA. That's the force. So forces are usually not constant over a period of time. So we use the average of the force over the time it acts. The law of the conservation of momentum is written as the total momentum is going to be constant before the collision and after the collision, as long as there is no external force acting and friction is negligible. So in an isolated system, the net force must equal 0 and friction must be negligible. And the conservation of momentum would apply only when the net external force is 0. Elastic versus inelastic collisions. If the object separates after impact, the collision is elastic. If they stick together, the collision is inelastic. Kinetic energy is conserved in an inelastic collision, but not in an elastic collision. We talked about that. So the approach to solve a two-dimensional collision is to choose a convenient coordinate system, x versus y, and break the motion into components along the perpendicular axis, as in here. Choose a coordinate system with the x-axis parallel to the velocity. So that's the velocity. We need to get the parallel x-axis and solve for that. the two-dimensional collisions of the point masses where mass 2 is initially at rest. So we conserve momentum along the initial direction of mass 1 or the x-axis and along the direction perpendicular to the initial direction or the y-axis. There are point masses that are structureless. These point masses are structureless particles that cannot spin.